Like and subscribe.
Welcome back, guys.
If we can hit 300
This is
subs
Mr.
by
Pata.
next video, by next
Dun,
year,
dun.
doing a
He's at like 285.
Before you even watch the video, make
Yeah,
sure
I
to
know.
like and subscribe, even though they have no
You should
idea
do a
what
giveaway.
content.
We're doing a giveaway.
It's 1 year students of 5 on
Wait,
this.
do you have a Facebook?
One lucky student, one lucky subscriber will get a 5 on this year's AP.
Alright,
What automatic E?
Dun, dun.
Hey, I'm
All you have to do is pay me $50 to be a part of this video.
one of the things,
What's up?
one of the things that we do here is, when we see a problem, the thing we're trying to do is say, which one of the frameworks, right, which one of our conceptual frameworks do I think I'm going to need here? I'm looking at this, I see a spring.
Sorry.
Okay, I see a spring, so I'm already thinking there's probably got to be some energy stored somewhere, right?
True.
Does that make sense?
Yeah.
I also am noticing some giant dots down here,
Force.
so I'm probably going to need some force diagrams. I'm also seeing multiple blocks together,
Oh.
so I'm thinking of collision, so what am I going to have to apply here? Momentum. You see what so this is what I'm doing when I'm approaching any problem, like, what are the things I think I'm going to need? Okay? Now there is something here that's going to be interesting. Do you notice how this spring here
There's some geometry.
is a little jacked up?
That's a little jack.
Okay.
Little jack.
Makes sense why you're
Because I'm
crazy.
so short.
Hey, where'd it go?
Yeah.
You're like 5'11".
Where'd my problem go?
Get right.
6 foot and a quarter.
You are
actually.
not. We measured.
Wait, Sean, are you?
You were definitely 5'11".
You
thought.
We measured in AP Lit.
Like,
Yeah, no, 6 foot.
Were you though?
I'm not
The doctor
joking.
walks in and
I'm not
Jack, I
joking.
have some unfortunate
I know.
cancer.
You're
You're 5'11" and 3/4.
I don't need a valid.
The fact that this is gonna be on your YouTube forever.
So one of the things that I actually wanted to mention, and I'm going to go back and mention, is we need to be able to figure out like the relationship between the force function and the energy function, right? So for a spring specifically. So let me pause on that, and we're going to go back real quick, because I think that we're going to need it here.
I work at 6:45.
where are you at?
At work.
At work, thanks. I work at my work.
Yeah.
Okay.
Mr. Patty gets to read through a bunch of crappy SAT.
Oh, Mr. Patty,
Congratulations.
do you need to talk about?
I'm really proud of you.
Thank you.
Do you
Though.
I just keep
make
thinking that paycheck.
Technically,
It's you bring it.
Yeah, that's a good one.
All right, watch close.
I'll make my boss.
So this is the force. This is the force on a spring. That's all right. You can handle it. There's a force on a spring.
I can't do it.
Okay. When I graph this, this is the stretch distance. This is the force. I know that this is going to be linear with a zero intercept. I feel really good about that. Where's the energy stored? Okay. It's in the spring. On this graph, it's the area. True. Right. So the work done on the spring is equal to the area of the force dx function. Okay. What's the antiderivative algorithm?
Add 1 to 5.
It's kx dx, right? So this is x to the 1. So add 1 to the exponent and then divide by the new exponent. Is that cool? So this is equal to kx squared over 2. I'm pretty happy about that. So this is the work done, right? And this is also the energy stored in the spring. And that's where we get this equation that we saw over here, 1/2 kx squared. See how that works?
Yeah.
All right, so that's where that equation comes from. Now, this is for a linear spring, right? And we're able to put x to the 1, do the thing, and Bob's your uncle. But this statement is true for any spring. This one we have using here is just a linear spring. Is that cool? So now let's go back to here. And what do you notice about the spring? See how it's fat here and skinny here? that's giving you a pretty good indication that,
It's not linear.
thank you, that it is not linear.
Will they tell you?
I didn't even know there was no such thing.
Okay, they do. So now that we've looked at the surface features and tried to say like, these are things I think I'm gonna need, let's see if any of that is true, okay? A block of mass 2m rests on a horizontal frictionless table and is attached to a relaxed spring as shown in the figure above. The spring is non-linear, okay? And has the function f is equal to negative bx cubed. What does the negative mean in this context?
Since the force, the force that the spring is exerting back on what is applied to the spring.
Good, that's exactly right. So this is, the spring is non-linear and exerts a force that's opposite the direction of the compression. So if it's compressed, it's pushing out. If it's stretched, it's pulling in. Okay? Where B is a positive constant, X is displacement from equilibrium for the spring, a block of mass 3m with initial speed V0 is moving to the left as shown. On the dots, which represent the blocks of mass 2m and 3m, draw and label the forces. Do not put any components on. That act on each block before they collide.
So how about that weather?
Wonderful weather we're having.
Wait, can you explain that?
Yes.
See,
So
the people
the
that
spring
did
exerts a
talk
force
about
that's
what
opposite the direction of the displacement. So if you push the spring in,
They
I don't
just
know.
don't.
it's pushing out.
So it's basically kind of like, this is mostly for a spring thing because like,
Yes.
you don't really see this in gravitational, nor do you see it in any other like.
Well, that's
Well,
right.
As
there's
in
a
United
force
States.
by the gravitational field,
What?
right? The force by the gravitational field is always down.
It's a
So if the
world
block
really
was
good.
moving down,
Like
that would be a positive work done by the field.
Kind of Mars.
But if the block was moving, that would be a
That's
negative
like
work
that.
done by the field. But this negative thing is for forces because the force can change based upon the displacement. Gravitational force is always down.
We want you.
All right. So this is weird. Okay, this is weird because when I look at this, all of a sudden I'm looking at it going like, ah. So
That's exactly how I feel every
attach
single
relax
time.
spring shown.
Meter
So
dimension.
this is block 3M. Yes? Does the Earth pull it down?
Yes.
Yeah, you have-
3mg. And what is the table doing?
Push up.
The normal force?
Okay, shut up.
Is that cool? Now it's moving left, but what do you notice about the table? It's frictionless. Are there any other forces?
No.
No. Sometimes they're easy.
That's why Common Core sucks.
Okay?
Either make it hard or make it easy.
What about this 2m one?
Same, but different.
Is it compressing the spring?
Exactly the same.
No, see, it says here, it's attached to a relaxed spring as shown in the diagram.
Whoopsie.
And it also says that it's at rest on a horizontal.
Oh,
A
yeah.
block mass 2m rest.
I don't know, I just think it's this.
I concur.
Who?
Yeah.
So if it's a relaxed spring, why is it negative?
So it says it can exert a force if you had a compression.
Oh, okay. So, yeah.
Cool?
Yeah.
All right. You guys feel okay about that?
Oh, I feel great.
Yeah.
All right.
That's like when you're in math class and it's the first example and you're like, is this like how it's easy it's gonna be? No, it gets harder.
No.
The first page of every.
The first page of every single.
I hope there's a lot of force.
Right, it's always like when I'm studying, I don't even go next, so like, it doesn't even, it's so much easier that it's like.
The two blocks collide and stick together. All right. Where are you right now? The two blocks collide and stick together.
It's the
That is
last.
absolutely a momentum problem. Okay? You're going to use both blocks as your system. All forces are going to be inside the system. Momentum is conserved. That's it.
Is
Okay?
it an elastic since it sticks together too?
That's an inelastic collision, so we're going to go with,
So we understand.
so the PI here,
6-0. Softball left, lost 1-0. Who lost 6-0?
Yeah, baseball wins this one?
What's the initial momentum here?
It's the
Zero?
momentum
Oh,
of the one block going B0.
So, this is an important thing though. Which way was that block moving?
Going to the left.
It's moving to the left, so the initial momentum is negative 3mv0. And then what about after?
Maybe 5M.
V final.
Yeah.
Okay.
Well,
Would it still be negative?
Would this be, are you doing B right now?
So we're just gonna solve for it here.
Okay. Just
Okay?
doing conceptual framework.
Oh,
It's,
okay.
when you solve for it, it's gonna be negative,
Right.
right? Yeah.
Oh, so then V is literally driving expression for the final.
Yeah, so B says like, what's the final velocity? Then C says determine expression for the kinetic energy of the two black systems immediately after the collision. No problem, because the final velocity here is negative 3v0 over 5, right? Because the m's magically disappeared. So how would you express the kinetic energy then?
You use that and square it, and then 5M, yeah.
So is that 5 over 2?
Is that all you would need to write?
Yeah.
Oh, I wouldn't have to.
I mean, you would have started with kinetic energy equal to 1/2 mv squared, and then you go to this. This is probably actually just a one-pointer, to be honest with
Okay.
you. Like,
Yeah.
just jump right to that.
Is that for C, right?
That's for C.
Yeah.
So, the thing about this is that this is a multi-part problem where we had to start with forces as our framework, then we moved into
Oh.
momentum as our framework, then we moved into energy as our framework, right? But we're well versed in how, like, the kind of the surface features that allow us to choose which one, right?
Yeah.
Okay. Now D is interesting because D says, what is this, by the way?
5 would cancel 25.
So I got- so
it'd be one.
And on the AD test, if we left it like that.
9 over 10?
And B0 and
9/10?
yeah.
9. Yeah.
If we left it like that, will we get the point still?
No. Maybe. I don't know, actually.
So
Try to
simplified.
simplify if you can. Is that cool? Now, it says derive an expression for the maximum distance the spring is compressed.
Well, that's X, right?
Okay, yes, we're gonna solve for the x here. I find this actually kind of interesting because there's something kind of hidden here. Okay? There's something kind of hidden here. The two block system then compresses the spring a maximum distance d is above. Now, if you compress it the maximum distance, what can you assume is true about the speed of the blocks at that moment?
0.
0. So how much energy goes into the spring?
All of them.
All of this.
Because there's 0 kinetic energy.
So that is
That's
equal to
K,
UG.
1F.
So, well, no, see, here's the problem, because we have a non-linear
Oh.
spring,
Oh.
So
right?
you can't use 1/2 kx.
So
Oh,
we can't
we
use
use the
that.
work with-
So we do know, though, that the work done
Yeah.
is equal to the area of, is it bx cubed?
Oh, negative,
Yeah, negative.
but, yeah.
Right? Now, I know it's negative, right? I know it's negative, but I'm talking about the work done on the spring, not the work done by the spring. So I'm gonna leave the negative out, okay? And how much work was done? Okay,
Oh, because that's a change in energy because since kinetic 0.
Well, since energy is conserved in this case. 9 over 10 is.
so when I go to solve this though, what are the bounds of my thing? It goes from 0 to d, right? So I have to apply the antiderivative function here. So this is going to be bx to the fourth over 4 from 0 to d. Is that cool? And we don't need to solve this. Move on with our lives here. My point is that you asked me like, what does it look like if I'm gonna sit down and do one of these? And what I'm gonna do is, I'm gonna say like, what do I think I need to do here? Those are force diagrams, I'm gonna draw. This is a collision, I'm gonna use momentum. This is a spring, I'm gonna use the energy. Right?
This is a distance problem, would be more work.
Well, if it's a projectile motion problem, something flying through the air, I gotta use my projectile motion framework,
Which is kinematic.
which is kinematics, right?
But if it's a force problem with asking for distance d, that is work.
Absolutely. Okay. In which direction is the net force, if any, on the block mass 2m when the spring is at its maximum compression?
Oh, wait, isn't that,
Well,
Well, it seems
velocity
too
is
obvious.
0.
isn't it 0 because the block's at,
Yeah.